Have you ever just stopped and wondered what's actually going on inside the mind of an AI like ChatGPT? Well, today, we're pulling back the curtain to see how they really work. And the secret sauce? It's a revolutionary piece of engineering called the transformer.
You know, we've all seen them generate stories, answer these super complex questions, even write code. But how do they go from just a string of text to genuinely getting the meaning and the context? It honestly feels like magic sometimes, but I promise you, it's not. It's just some seriously clever engineering.
And here's the crazy part. Believe it or not, the entire mind-bogglingly complex behavior of a large language model, it all boils down to one surprisingly simple task, just predicting the very next word in a sentence. Yeah, that's it. All that intelligence, all that creativity, it all comes from getting exceptionally, unbelievably good at just this one thing.
So to really understand how this works, we're going to follow a piece of text on its full journey right through the model. Think of it like an assembly line for meaning, where each step refines and enriches the information until a final product, that next word, is ready to go.
Okay, first things first. A computer can't read words like we do. We have to translate them into its native language, which is, of course, numbers. So we do this by turning every single word into a long list of numbers, kind of like a unique numerical fingerprint, and this is called a vector.
Right, so each word in the model's vocabulary gets mapped to this unique list of numbers called an embedding. Now, this isn't just some random ID number, it's actually a coordinate that places the word in this vast, multidimensional meaning space, where words with similar meanings are located close to one another.
And this is where things just get wild. The model isn't just storing definitions, it's actually mapping out relationships between ideas. Just look at this equation. If you take the vector for king, subtract the vector for man, and then add the vector for woman, you land almost exactly on the vector for queen. The model has learned a direction in space that literally represents the concept of gender. This is math as meaning, and it's incredible.
So, a word's initial embedding is a fantastic start, but it's context-free. The meaning of a word can change dramatically based on the words around it, and the model absolutely needs a way to figure that out.
Just take the word mole. In these three sentences, it means three completely different things, right? An animal, a unit of measurement, a spot on your skin. But at the start of our journey, the vector for mole is identical in all three cases. And that is a huge problem the model has to solve to make any sense of the text.
So, how does it do it? Well, this is where the real innovation of the transformer comes in. It's a component called the attention mechanism. This brilliant process allows the word vectors to essentially talk to each other and pass information back and forth to refine their meaning based on the full context of the sentence.
So how does this talking actually work? Well, for every single word, the model creates three new things. A query, which is basically the word asking, hey, here's what I'm looking for to understand myself. Then there's a key, which is another word's response saying, well, here's what I am. And finally, a value, which is the actual information that word has to offer. It's like a room full of words all trying to find their most relevant partners.
The whole process is basically a matchmaking game. Each word's query checks out every other word's key to see how well they match up. The better the match, the higher the attention score. These scores then decide how much influence each word's value, its actual meaning, gets to have. And the end result? Each word's original vector gets updated with a blend of the most relevant information from all the other words in the sentence. It's that simple.
Okay, so now our vectors understand their immediate context. The next step is to pass them through the model's vast internal library to access stored, factual knowledge about the world. This is where all that memorization from training comes into play.
And this component is known as a multi-layer perceptron, or MLP for short. And research suggests this is where a huge portion of the model's factual knowledge, all the things that it has memorized from its training data, is actually stored.
So you can think of the MLP as this massive collection of super specific if-then statements. As you can see here, one tiny part of it might learn to activate only when it sees the concepts Michael and Jordan together in a vector. And when that happens, it knows to add the concept of basketball to the mix. That's how the model connects the dots and accesses all the facts it has memorized.
All right, let's bring it home. We've seen the two core components, attention and the MLP. Now we need to see how they all build up to an actual prediction. It's all about layers and scale.
So these two pieces, the attention mechanism for figuring out context and the MLP for looking up knowledge, they get bundled together to form a single transformer block. This is the fundamental building block of the entire network. But modern models don't just use one of these. Oh no, they stack them. GPT-3, for instance, has 96 of these blocks, one right on top of the other. As the vectors pass through each layer, they can develop more and more abstract and nuanced understandings, building on the work of the layer that came before it.
And the scale here is just staggering. GPT-3 has 175 billion parameters. Think of them as tiny little dials that get tuned during training to store information. And as you can see, about 2/3 of those dials are in the MLPs. That's the model's huge library of facts. The famous attention mechanism, which handles all that context, makes up the other third.
Finally, after a vector has passed through all 96 of those layers, gathering context and knowledge along the way, the final vector in the sequence is used to make the prediction. It now contains all the information needed to calculate the probability for every single possible word that could come next.
This brings us to a final, and honestly, a truly mind-bending idea about how these massive models manage to be so efficient at storing information. The embedding space has a fixed number of dimensions, right? Let's say it's 12,000. So how in the world can it possibly store millions and millions of different concepts?
Well, the leading theory is a concept called superposition. Imagine you're trying to store things in a warehouse. If you insist every single item gets its own, perfectly separate, walled-off space, you run out of room pretty fast. But what if you let them overlap just a tiny, tiny bit? Superposition suggests the model does exactly that, storing concepts in directions that are almost separate but not quite. This tiny bit of noise allows it to pack an exponentially greater number of ideas into the exact same amount of space.
And this strange property of high-dimensional space, it could be the secret key to this entire AI boom. It helps explain why making models bigger doesn't just make them a little bit smarter. It leads to these dramatic, unexpected leaps in their abilities. More space doesn't just mean more storage. It unlocks exponentially more potential. Which leaves us all with a final, fascinating question. What new intelligence is waiting to emerge when we decide to scale them up again?